Yeah, welcome to this week's APRG seminar. Today we have Shyam Swarup Mondal from ISI Kolkata, and he will talk about orthonormal Strichartz estimates on abstract measure spaces. Yeah, can start now.
Yeah, Good afternoon, one and all present here. So, firstly, I would like to thank the organizer of this APRG seminar group for giving me this opportunity to present my work. And the main aim of this talk is to extend certain well-known inequalities from single to a system of orthonormal functions. So, it's interesting to note that in the nonlinear dispersive partial differential equations, there are mainly two types of tools available to estimate. One is Strichartz estimate, another one is a smoothing estimate. So Strichartz estimate mainly tells about the LP-LQ space-time bound of the solution, while the smoothing estimates tells about the Sobolev L2 space-time estimates of the solution. That is, smoothing estimates allows us to gain derivative even if the solution initial condition don't have any regularity. So in my talk, in the first part of my talk, I will tell about the Strichartz estimate. I will recall some of the well-known Strichartz estimate and some literature review regarding the orthonormal versions. Then I will move to my topic, orthonormal Strichartz estimate for general self-adjoint operator. And the next part of my talk, I will tell about smoothing estimates for some particular type of
Sam,
operator.
sorry
Yeah.
to disturb you. I think some echo is coming from your side only. Probably you are
Oh,
opening two things. Or no?
no, only I am using my headphone and one
Okay,
computer.
okay,
I don't know.
okay, okay. I see some echo. I hear some echo. That's why I disturbed. Okay,
Okay,
that's okay.
now is it fine or
Yeah,
is it
is it
fine now?
fine? Okay, yeah, okay. It is. It can be. Okay, okay.
Okay,
Yeah,
I don't know
continue.
what's happening here.
Okay,
Okay.
yeah, yeah. Continue.
Yeah. So in the next step of my talk, I am going to discuss about smoothing estimate for some particular type of operator, and we'll see some orthonormal version. And at the end, we'll relate this orthonormal smoothing estimate with restriction problem. So let's move to the main part. So consider the free Schrodinger equation on Rn associated with the Laplacian, and the initial value is given by f. So it is well known that the solution of this system is given by u equal to e to the power it delta f, and it also can be written in terms of convolution. So since the solution can be written in terms of convolution, it satisfies L1 L infinity norm with time decay t to the power n by 2. And since this operator is a Hilbert's unitary operator, it also satisfies L2 L2 kind of norm. So using the Rees-Soreen interpolation between this L1 L infinity and L2 L2, we have that the solution satisfies this type of dispersive estimates. That solution's LP norm is less equal to initial conditions LP dash norm with this decay. Moreover, Strichartz in 1977 proved that the solution of this free Schrodinger equation satisfies this mixed LPQ norm. For PQ greater equal to 2, and if it satisfies this admissible condition such that dpq cannot be simultaneously 2 infinity and 2, then the mixed LQP norm of the solution is less equal to 2 norm of F. So initially, the Strichartz proved these estimates when P equal to Q using the restriction theorem for paraboloid surface. However, for other points like rather than these diagonal points, below he proved all other points except the endpoint cases. And endpoint cases means when Q equal to 2 and the P can be found from this inequality, and when Q equal to infinity, these two cases and all the endpoint cases covered by the paper of tau. Okay. So, and similarly, if we consider the wave equation on Rn with the initial condition f and g, then it's well known that the solution is given by in terms of sine and cos. And Guinevere Velo, they proved that if PQ satisfies this D minus 1 admissible condition with PQ greater or equal to 2 and QPD cannot be simultaneously 2 infinity 3, then the solution of this wave equation satisfies this type of estimate, and A is equal to, here the Sobolev norm A is equal to D by 2 minus D by P minus 1 by P. Okay. So now coming back to the Schrodinger case, this is our main interesting part of this talk. Consider the Schrodinger case now. Suppose this one is for the single function. Okay, there is only f in L2 is involved. Now suppose fj are orthonormal function in L2, and consider this summation j e to the power it Laplacian fj square, its mixed LQP norm. So we can ask, is there an inequality for this left hand side sum? Okay, one obvious answer is that if we apply triangle inequality, and if we use the Strichartz estimate for single function, we can find that this norm, left-hand side norm, is less equal to n to the power p without capitalizing any kind of orthogonality of fj. Okay. So the natural question is, can we, if we use the orthogonality of fj, is it possible to get a better estimate than n to the power p? So the answer is yes, we can get a better estimate. And if we capitalize, then take the finite sum j equal to 1 to n, then one can see that this inequality is less equal to n to the power p times q plus 1 by 2q. By capitalizing that fj are the orthogonal family in L2, note that if q is greater than 1, then q plus 1 by tq, this term is strictly less than 1. That means the exponent p times q plus 1 by 2q is strictly less than p. That means we are getting better scaling result in terms of number of function. And one can ask whether this p times q plus 1 by 2q, whether this one is the optimal, or we can get a better estimate than this. So regarding all the question, our aim is to discuss extended version of Strichartz estimate, taking of the form this mixed LQP norm of summation nj e to the power it delta fj square is less equal to the Schatten norm of nj, where fj is a system of family of orthonormal functions and nj is a subset of C. So our aim is to investigate such type of estimate, and we call this one as the orthonormal Strichartz estimate. We will find the value of p and q so that this estimate holds, as well as for what the optimality of this lambda. This Schatten norm L lambda is nothing but set of all compact operators on A on L2, such that the singular value of A lies in the small L lambda space, and its norm is given by as usual form. So coming back to the question for the Schrodinger equation that we asked, whether this n to the power p times q plus 1 by 2q is the optimal one or not. Regarding this question, Frank and some of the co-authors, they proved that
So,
if q, yeah.
some in the
Mhm.
previous slide, these FJs are these forms have complete orthonormal basis or any orthonormal just system. I don't
Any
get
orthonormal basis,
means
yeah.
complete. I mean orthonormal basis or
No,
means
means what is
whether
meant by you are telling complete
whether
or
I am asking that whether span of this FJ which dense in
mhm.
L2 or D or
No,
you
no,
are
no,
not
no, no, we don't need
just
require all this for any
okay.
orthonormal system, yeah.
Okay, only that means linearly independent and norm of fj is really one.
Exactly,
That's one.
yeah.
That's one. Right. Okay.
Huh. So regarding the question we asked for Schrodinger equation, the Frank and some of the co-authors, they proved that if PQ satisfies the same admissible condition as in for the single function, and then for any orthonormal system in L2 and a sequence nj subset of C, if P lies between 1 to d plus 1 by d minus 1 and lambda equal to 2p by p plus 1, then this orthonormal inequality holds. Okay. And here one interesting point is that this lambda equal to 2p by p plus 1 is the optimal one, in the sense that this inequality fails if for lambda is greater than 2p by p plus 1. And it's true for any lambda get less equal to 2p by p plus 1, obviously. Moreover, if this inequality also fails at the endpoint p equal to d plus 1 by d minus 1, when lambda equal to 2p by p plus 1. Okay. So this inequality true only for this range of p when lambda equal to 2 by p plus 1. And this range of p 1 to d plus 1 d minus 1 is far less than for the range that we already saw for the single function. So there is one can ask another question, is it possible to extend this range p if we change the value of lambda? So regarding this, they also proved that yes, it's possible. If p lies between d plus 1 by d minus 1 to d by d minus 2. Note that d by d minus 2 is the endpoint case for the single function. So if p lies between d plus 1 by d minus 1 to d by d minus 2, then this inequality 1, orthonormal inequality, holds for any lambda which is less than q. Okay. They also prove that if lambda is greater than q, then this inequality fails. Okay, that means here q is the optimal one. And if lambda equal to q, then they prove that it satisfies some weak type of estimates, not the strong type. So we can see this in graph in a better way. If we take the 1 by p and 1 by q graph, then Frank and all his co-authors, they first proved that the inequality is true from 1 to this diagonal case f, diagonal point. And they used this operator theoretical approach to prove this inequality. But it was missing from A to F. They mentioned that this inequality will true even for A to F interval, but they are unable to solve this. And later, Frank Sabin, they proved this complete range using the restriction theorem argument. And they also proved that this inequality also hold from A to D, but the certain norm will be now less than Q for any lambda less than Q. Okay. So the motivation to extend functional inequalities from single function to orthonormal set of orthonormal functions came from many-body quantum mechanics. In quantum mechanics, a system of n independent fermions can be described by a collection of n orthonormal functions in L to Rn. For this particular reason, functional inequalities involving a large number of orthonormal functions is important to us. And the generalizing functional inequalities involving from single to orthonormal function is not a new topic, and the first initiative work in this direction goes back to the work of Lieb and Thring. What they did, they first extended the known Gallardo-Nirenberg-Sobolev inequality to its orthonormal version. And Frank and all, they first proved they first generalized the Strichartz inequality from single function to system of orthonormal functions. And for the last, I think, 4 and 5 years, a lot of research is going on in this direction of orthonormal inequalities. It's not possible to mention all of them, but I mentioned some important, which are, if we considered in the paper of Beige and uh, the co-authors, they considered the Schrodinger equation, but the initial condition they taken from the complete regularity, and then they've extended the orthonormal Strichartz estimate. One can see this second paper. It's about orthonormal Strichartz estimate on torus, and similarly the third one is for compact manifolds. We also studied in this direction for the Hermite and the special Hermite operator case. But in the paper of program math sigma, recently Beige, Lee, and Nakamura, they also extended orthonormal Strichartz inequality for wave equation, Kelvin-Goddard equation, and fractional Schrodinger equation by introducing different type of oscillatory integrals. And recently, we also extended this type of orthonormal Strichartz estimate for generalized Laguerre operator, Dunkel operator, and all those. With dispersive equation with potential in this direction, the Strichartz estimate from single to orthonormal can be seen by the paper of Hoshia. And we also extended for the Dunkel framework when we consider full regularity. And the most recent paper is done by Dibbang Bhimani and his students. They extended the Strichartz estimate from single function to system of orthonormal function in the framework of waveguide manifold. So Strichartz estimate not only studied in this particular type of F basis, but it also studied on a more general measure base, abstract measure base. The tau and Kiel and tau, they consider x mu, this x as a measure base and h via Hilbert space. And for each t belongs to R, suppose ut is a bounded linear operator. No, ut is an operator from H to L2 that obeys the following two conditions. That for all t and f in H, UTF L2 norm is less equal to H norm of f. And UT also satisfies this type of L1, L infinity type of estimate. Then under these two assumptions, they prove that if PQ greater equal to 2 and PQ sigma is simultaneously not equal to 2 infinity 1, and if PQ satisfies this admissible condition that 1 by Q plus sigma by P equal to sigma by 2, then this UT satisfies this type of Strichartz estimate. UTF, its mixed LPQ norm is less equal to 2 norm of H. So our motivation was to extend this orthonormal Strichartz estimate from single to set of orthonormal functions. But we'll not consider exactly this same UT. We'll consider a particular case so that we can unify almost all the existence result available in the direction of orthonormal system. Okay, so for this we consider x d mu be a measure
Sam,
base. Yeah.
Sam, what is sigma here? Is the dimension of
Okay. Sigma depends on dimension. For the Schrodinger case, if you consider, then sigma will be d by 2. And if we consider the wave case, then sigma is equal to d minus 1 by 2. So it will depend on the dimension, okay?
is
In
it
particular
related to the
cases.
measure space? What measure you were taking?
It's okay. Okay. No, it's not related to any measure. For some sigma greater than 0, the decay estimate satisfies such type of estimate. There exists
Okay.
some delta greater than 0, okay?
Okay. Okay.
Yeah. So we want to unify all the existence result, okay? So for this, we consider x d mu be a measure base and L be a non-negative self-adjoint operator on L2. We considered this Schrodinger equation associate with L with this nonlinearity term f with the initial condition u of 0 to equal to f of x. Then by Duhamel principle, we know that the solution of this system can be written in terms of e to the power it lf minus this term. But in order to extend from single function to orthonormal function, we need some condition on the semigroup e to the power itl. So we assume that this Schrodinger semigroup e to the power itl is an integral operator with kernel KIT that satisfies this type of uniform decay estimate t to the power minus alpha by 2. Okay, so this kernel assumption is required in order to extend from single to orthonormal system. But it's important to note that tau, Kiel and tau, they consider the general operator ut on L2. But if you give some extra condition on the space X, such that suppose X is a separable measure space, then by Danforth and Patty's result, one can also see that such type of operator becomes an integral operator with Schwarz kernel satisfies some L1 L infinity norm of this. So one can also study using some other assumption on the space for the general operator. But in order to unify all the existent result for the Schrodinger case, we consider particularly that self-adjoint operator associate on the measure space X. And there are plenty of operators that satisfies such type of kernel estimates. So in particular, if we consider Laplacian on Rn, then alpha will be D. If we consider Hermite operator, then alpha will be same D. For the twisted Laplacian, alpha will be 2D. For K generalized Laguerre operator, alpha will be this quantity. Even for discrete Laplacian on ZD, it will be alpha equal to 2D by 3. So we want to extend the Strichartz estimate from single function to orthonormal functions for this Schrodinger semigroup. And since this kernel estimate also satisfies Kirchhoff's condition, from Kirchhoff's result directly we can say that this e to the power ITLF satisfies this type of Strichartz estimate for the same value. PQ satisfies this admissible condition, as well as PQ n cannot be 2 infinity and 2. We extended this Strichartz estimate for single function to system of orthonormal function by assuming that the operator e to the power ITL is the integral operator and its kernel satisfies uniform decay condition. We proved that if PQ greater equal to 1, such that PQ satisfies this admissible condition now, then for any orthonormal system of orthonormal functions Fj in L2 and the sequence Nj in C, for P, if P lies between 1 to alpha plus 1 by alpha minus 1, and for lambda equal to 2p by 2p plus 1, this orthonormal inequality holds. And we are not claiming that lambda equal to 2p by p plus 1 will be the optimal one. It's hard to prove in the general measure case and even the endpoint cases. But we can guess from the example earlier that these two can be the only possibility. And also, depending on the value of alpha, there will be value of p such that this inequality will hold for any lambda less than q. Okay. We will prove this inequality. We will prove the inequality 2 and the next part, like these three quantity, will directly follow from the inequality 2 using some interpolation theorem. So in order to prove inequality 2, we need two kind of important tools. One is duality principle, like we will prove an inequality which is dual to this. But here, what is meant by dual of this inequality? So first we proved one duality argument. Then using the duality argument, we proved this inequality by applying like continuously the Stein complex interpolation theorem. So, okay. So in order to prove, the duality principle states that if A is a bounded linear operator from L2 to LQ dash P dash for some PQ lies between 1 to 2, then the following two are equivalent. Now you can see that the first inequality, this one, is the orthonormal Strichartz estimate, and the second one is its dual version. So we will prove this dual version instead of our first original Strichartz estimate, orthonormal. Here it's important to note that all the orthonormal Strichartz estimate to prove directly is still open problem. Only Rumin recently proved directly the life-threatening inequality. Otherwise, all the orthonormal Strichartz estimate proved via a duality argument, not directly. Okay. So using this duality argument, first we prove the inequality for the range 1 plus 2 pi alpha That means from the diagonal to the endpoint up to endpoint type alpha plus 1 by alpha minus 1 in this interval. So using the duality argument, it's enough to prove this inequality for the value of p when it's lies between alpha plus 1 to alpha plus 2. So in order to prove this inequality, we will introduce an analytic family of operators. Then for different value of the real part of z, we will find two different inequality. And then we will interpolate between these two inequality, we will get the original one. So in order to form the analytic family of operators, we consider the T epsilon. The T epsilon is an integral operator where the kernel is given by this quantity. KIT is the original kernel of the operator with multiplied by this characteristic function. And for z belongs to C, with a real z is lying between -1 to lambda 0, where lambda 0 is a positive, we define another kernel kz epsilon is given by t to the power z k epsilon. Okay. And let tz epsilon is the corresponding operator of this kernel. Then one can see that this tz epsilon is an analytic family of operators, and the kernel also satisfies this decay condition, the t to the power lz minus lambda 0. So we want to estimate two inequality. So first we consider W1 tz epsilon W2. W1 W2 nothing but the multiplication operator, and since tz epsilon is the integral operator, we can find that kernel of this operator. And since we are calculating L2 norm, we are done. Like we know the kernel, and L2 norm means we only need to calculate the integral of k xy kind of. And if we apply the kernel estimate, then at the end we have to apply Hartree-Littlewood-Sobolev inequality to get the inequality 3 for real z lying between this interval. Now this one is one inequality. We need another one. So we'll choose the real part when real z equal to -1. The tz epsilon, we can see that tz epsilon can be seen as a Hilbert transform of some operator kind of, and tz epsilon is bounded with some constant depending on the depending only on imaginary z. This is coming from we need some calculation here. Like there are some calculation to see that tz epsilon can be seen as a Hilbert transform, and using the boundedness of Hilbert transform, we can say that at a real z equal to -1, this inequality holds. That means L infinity norm of W1 tz W2. L infinity means only bounded. And since tz bounded, it will come like this. Now, this two inequality is true for tz epsilon, but we don't need z here now. So we prove for the real z equal to -1, and where real z is lying between some positive quantity. So we will counter the 0 of z equal to 0, and we will apply the Stein complex interpolation. And at the end, we will also take epsilon tends to 0. Then if we do all three steps, we will get our required inequality. Now the remaining part is if p lies between 1 to 1 plus this diagonal. Okay. Now if you notice, when p equal to 1 from the admissible condition, q equal to infinity. That means if here it will be L infinity L1 norm, and this is trivially true for lambda equal to 1. Okay. So again, we will interpolate between these two, like for 1 infinity, and for the diagonal case, we can cover from 1 to whole that alpha plus 1 by alpha minus 1. Now this here, another important thing is that this inequality that LQLP is true for any QP which satisfies the Strichartz estimate for single function, not only for q equal to infinity, p equal to 1. In particular, this inequality is true at the endpoint also. So here it says that it also holds for the Kiltau's endpoint. Okay. Now in the second part, when we considered the different value of alpha and for the different value of p, then the orthonormal inequality also holds. So it will, if we consider alpha greater than 2, then we just need to interpolate between if QP is 1 alpha by alpha minus 2, that means one endpoint, and another point QP equal to alpha plus 1 by alpha plus 1 divided by alpha minus 1. Note that if P equal to alpha plus 1 by alpha minus 1, at this point when lambda equal to 2P by P plus 1, the inequality fails initially. So we will choose a arbitrary close point to this QP. It's not exactly QP, but arbitrarily close to QP. Then we can interpolate between these two, we'll get our required condition when alpha greater than 2. And similarly, for alpha equal to 2, we will choose two endpoint and close point to this. And for 1 to 2, again, we will choose one endpoint and one arbitrary point, which is close to this alpha plus 1 by alpha minus 1. Okay. If we interpolate between these 2 points for different cases, we will get our result. Okay. So we also extended Strichartz estimate for orthonormal version, but for a class of dispersive semigroup. Let phi be a smooth function and psi belongs to CC infinity. If we consider the truncated dispersive semigroup ut equal to e to the power it phi of L and psi of root L, then we proved, then under the same assumption that ut is integral operator and it is a kernel that has uniform decay condition, then we can prove using the same technique, this whole quantity. But here we note that UT, this dispersive semigroup, localized dispersive semigroup, is required to prove orthonormal Strichartz estimate with regularity, not in L2. So if we consider initial value from the HS space, then we need this dispersive orthonormal estimate. Okay. And one can see that if we chase L equal to minus Laplacian, then alpha equal to D. And for this wave, so the frequency localized estimate, in these two cases, that all the two cases means this 4 and the next one, this one, all the holds. But for Hermite, delta K, or discrete Laplacian, and for other examples, the second condition was not proved earlier for any of the operators. So it will a more generalized version of the known results. And another thing is that one can see this orthonormal Strichartz estimate in a different point of view, and which is important in application part also, as well as to find the pointwise convergent result for orthonormal system. So in this direction, we need some operator theoretic approach here. Let gamma is the operator given by this, where the bracket notation means f goes to VAFU. We define gamma t as the evolve operator given by this e to the power ITL gamma e to the power minus ITL. Then we see that this gamma t solves this operator valued von Neumann Schrodinger equation with initial condition gamma 0 equal to 0. This particular von Neumann Schrodinger equation is important to study pointwise convergent for orthonormal system. And if we define the density function rho gamma t as e to the power ITL fj square, then one can see that this nj e to the power ITL fj square, this one was present in our orthonormal inequality. Then using the above notation, our orthonormal inequality will reduce to mixed LQP norm of rho gamma t is less equal to 2p by p plus 1 of the gamma. And if we consider an inhomogeneous system of the von Neumann Schrodinger equation type with a extra inhomogeneous term RT, which is a bounded linear operator on L2, then using the orthonormal Strichartz estimate, we can see that the solution of this inhomogeneous system satisfies this type of estimate. In particular, this type of estimates required to study the Hartree equation for infinitely many system. Hartree equation for infinitely many system will reduce to this operator value form with an inhomogeneous term. So on that case, this inequality is required. Okay. So this one is regarding the first part of my talk. And the next part, I'm going to discuss about some orthonormal smoothing estimate. As I already said, that in smoothing estimates mainly allows us to gain extra derivative of the solution, even if the initial condition don't have any regularity. So for gamma greater than 0, we consider a particular type of operator, W nu t, is given by e to the power I p phi of j plus x j phi double dash j to the power nu by t and f hat of j. This type of operator considered by Tau in his endpoint paper, as well as Vega in his paper. So this W nu is important. It has a it's important. It's generalized several known equation like Schrodinger, higher order. This W nu operator also can be seen in a different way. Like W nu t operator is a Fourier integral operator with phase function phi and the symbol phi double dash j to the power nu by 2. The this phi double dash j to the power nu by 2 inside this integral introduce a kind of regulation or smoothness of the operator W nu. How? If we consider phi of j equal to mod j to the power alpha, and let's say alpha is strictly greater than 2, then if we put here, then it will be phi double dash mean j to the power alpha minus 2. It will come out, and the remaining, if we put here phi of j equal to j to the power alpha, the remaining will be, if you denote u alpha t, is nothing but the solution of pre-Schrodinger equation, but with respect to higher order, with initial condition f. So if f is in L1 or something, then you can see that the solution gains derivative of gamma times alpha minus 2 by 2, but initial condition don't have any regularity. So that's why this W nu t in general called smoothing operator. And in order to study such type of W nu t operator, it's important to note that this p double dash j or the uh, phase function actually, this integral depends heavily on the phase function. So the class A we introduced here, means they introduced actually, the class A is the set of all assumption on the phase function phi, uh, such that we can analyze this operator W nu. Okay, we can analyze W nu so that we can apply the different methods like Van der Kerkhove method, stationary phase space method, or oscillatory integral theory to estimate this W nu operator. So this set of, there are set of assumptions here in the class. Roughly, they speaks about the critical points are actually finite of number. And at the critical points, you have the upper bound of phi double dash I, so that you can calculate or evaluate this integral efficiently. Even for infinity, asymptotically, phi double dash has a polynomial kind of bound. So these 5 conditions are required in order to find the decay or estimate this W nu t. Another important fact that this W nu operator is not in general form a semigroup. This W nu is not equal to W nu t plus s. Actually, it's W2 nu times t plus s. Even if it's not a semigroup, but it satisfies also almost all the property of satisfies due to this property. And if you see, if we consider phi of j equal to j square, if we take phi of j equal to j square, then there will be no, it will be constant on this case. And this W nu will reduce to the e to the power I t, only the Schrodinger semigroup usual. Since W nu operator satisfies almost all the conditions like semigroup, so Kenig-Ponce-Vega, they prove that this, if f is in L2, then W nu by 2, this operator satisfies this type of smoothing estimates. LQP is less equal to 2 norm of f. And obviously the function phi is from that class. If phi is not from the class, it may possible that this inequality may fail. In particular, if you take phi of j equal to log of mod j, and if you take nu equal to 1, then phi will not be in this class. And this inequality fails at particularly nu equal to 1, but for other values it will be true. So Kenig-Ponce-Vega, they proved this smoothing estimate for the particular value of P and Q given by 2 by 1 minus 2 and 4 by nu. So we extended this Strichartz estimate from single function to orthonormal function using the same idea as we already talked about for the general measure case. One important thing is that if we consider phi of xi equal to xi square and take nu equal to 2 by 3, then this smoothing estimate reduced to the classical Strichartz estimate proved by originally Strichartz for the diagonal case. Okay, so we extended this inequality from single to orthonormal function, and the statement is if P is lies from the class, nu is between 2 by 3 to 1. Initially it was from 0 to 1, but now it's from 2 by 3 to 1. And if TQ equal to the same value, 1 by 1 minus 2 to 2 by nu, then for any orthonormal system Fj in L2 and a sequence Nj in C, that mixed LPQ norm of some orthonormal, it satisfies this orthonormal inequality then for a certain 2p by p plus 1 norm. But this nu belongs to the range of nu norm reduced compared to for the single function, and this is due to the application of Hartree-Little-Wood-Sobolev inequality. So in order to prove, like we will apply the analytic Stein complex interpolation theorem, but we have to first construct the analytic family of operators. Earlier we defined by multiplying t to the power z with the kernel, but now t to the power z and with kernel it will not give our purpose, it will not satisfy. So we need different type of we have to define or construct differently, and so that it forms an analytic family of operators. For that, we define IZ is given by this factor where p double dash j to the power z by 2 is coming now. Then for real z equal to 1, it was proved by Vega that this IZ satisfies this type of estimate. But yeah, I am talking about now only on R dimension 1. We'll see for higher dimension also. So this IZ satisfies this type of decay condition. So we'll prove again by the duality argument. So to prove the original inequality using the duality, it's equivalently proved to prove this inequality. And the T nu is given by WW star, which is a integral operator with kernel defined by this I nu. Okay. In order to define analytic family of operators, first, as the earlier case, we will define T epsilon, which is nothing but the kernel with a multiplied by this characteristic function. Now, for real z belongs to 0, 1, we define this kernel kz epsilon by t to the power minus 1 plus z by nu. And nu is positive here, strictly. And tz epsilon is the corresponding operator. Then we can see that tz epsilon forms a analytic family of operators, and the kernel satisfies this decay condition when real z equal to 1. Since we have now the kernel decay estimates, we similar to earlier case, now we can prove to inequality when real z equal to 1, and for when we consider the real z equal to 0. So in these two cases, we have two inequality. We again will apply the Stein complex interpolation theorem. And now we'll consider z equal to nu, real z equal to nu. At this point, t epsilon will be t nu epsilon. And again, at the end, by tending epsilon tends to 0, we'll get the original inequality. So now we want to see what will happen for higher dimension. So if you can remember W nu initially for one dimension, it was defined that there is a second derivative involved in the integral. Now for the higher dimension, one problem is that what will be the analog of P double dash? P is lying from the class initially. So now the problem is what will be the analog of P double dash xi? By stationary phase function method, one can argue that we can replace this P double dash xi by Hessian matrix. But even for a real polynomial, it is very difficult to analyze what type of structure this Hessian matrix will be in the case of real polynomial. Forget about the general function. And it's very difficult uh, to actually analyze this W nu t even for a real polynomial to find the decay with respect to time. And it's also very difficult to recognize what kind of smoothness it will give. Like it says local smoothing operator or global smoothing operator. So regarding uh, this difficulty even for a real polynomial, but things will be very easy when we consider P to be real elliptic polynomial. Or if we consider P to be the summation of Pj type of function when Pj are one variable real polynomial. So in these two cases, it's easy to estimate W nu t. Okay? And the Kenig-Ponce-Vega, they proved that if nu is like between 0 to 2 by d, and for the PQ value 2 by 1 minus 2 to q by d nu, then W nu by t satisfies this type of Strichartz estimate. Okay. And we extended it for a system of orthonormal functions. We considered fj in L2Rn, and for the nj subset of C, we proved this inequality, but the range of nu reduced compared to the single function. This is again same. This is due to the application of Hardy-Littlewood-Sobolev inequality. And this is same. The proof is again same as the earlier case. So again, this smoothing estimates also can be linked with the restriction problem. Okay. The restriction problem is one of the classical problem in harmonic analysis. It says that if S is a subset of Rn hypersurface endowed with its d-1 Lebesgue measure, then the restriction problem asks for what value of P the Fourier transform F belongs to F in LP belongs to L2S. In other words, this inequality holds. This is the restriction problem. If we define the restriction operator as RS and ES as the dual of RS, which is extension problem, then the original restriction problem is equivalent to asking for what value of F. RS is a bounded linear operator from LP to L2. And since ES is the operator dual of RS, again, this is equivalently asking for what value of F is bounded from L2 to LP dash. So in the dimension one case, let A is equal to xi and phi of xi with the non-compact hypersurfaces of R2 with the measure this. Then if we calculate the extension operator ES, then it will reduce to this form, okay? And if we choose particular value of this capital F, like if we choose F from R to C such that F hat of xi equal to this quantity, and if we put here and calculate a few steps, we can see that ES nu is nothing but the W nu by 2 operator. Okay, so this restriction, not restriction, this extension operator actually reduced to the solution of the W nu t. It will reduce to the same W nu t operator. And we know the bound for this W nu by t from the Strichartz estimate. We already know the bound for such PQ. Using this, we can say that if phi belongs to this class and if nu belongs to 0, 1, and PQ equal to 2 by 1 minus 2, 2 by 4 by nu, then for F in any F in L2, such type of restriction estimates holds. And since we already extended this orthonormal Strichartz inequality from single to orthonormal for this W nu by 2 operator, then using the same condition, if we put instead of W nu by 2 to this extension operator there, then this will reduce to the orthonormal version of the restriction problem corresponding to this non-compact hypersurface. Okay, so yeah, these are the references. Okay, but the main reference are basically this first one and the second one, and I talked about from the contents of this my paper. Okay, and this one. Thank you.
Thank you very much for a nice talk. So, are there some questions from the audience?
The last question is for R. Okay, so Rn,
Yeah,
didn't you get that?
similarly, we can define the Rn also. I
You have
just
got some
gave,
result from this thing, right? For
yes,
Rn
yes,
as well.
yes. For Rn also. Again, like already told about the frequency localized estimate, if you can remember, then the frequency localized estimate is required to prove orthonormal Strichartz estimate with regularity. But in the middle step, there will be some weak type of estimates involved. Okay, so we also prove weak type of Strichartz estimate for single function. We extended for the orthonormal also. So in this paper, we extended from this inequality as well as weak type version as well as this frequency localized, and these two uh, restriction estimates. This one is for the R, but for Rn, it will be similar. We just need to define the measure properly.
Mhm. Okay.
Are there some more questions? Yeah, maybe there are no more questions. So let's thank Shyam once again. Thank you very much.
Thank you also.